Welcome back to the millimeter wave communication. So far we have talked about the transmit side beamforming in a MIMO case, right. Now, today we will be now moving to the, so today we will be covering the things that we will be covering are the following. Receiver side. So, what happens to the receiver side? So, if I summarize what has been the data model for the transmit side, you have already observed that it is nothing but say y bar t is equal to WBB, sorry, WRF and this probably the x vector. So, this is what my transmitter side. So, this is I would write it like a Tx side. Now, let us understand what happens when it goes through the channel and it comes to the receiver side. Now, if it goes to the channel, so let us say I am at the transmitter. Now, I have already propagated the signal through the air. So, what happens? How exactly the propagation happens? So, I do not draw all the antennas, but probably a few symbolic antennas, and these are all NT number of beamforming antennas, right. And if I see the beams, so this will be multi-level beams will be there. So, m number of, if there are m number of data, m number of beam splitting you want to do, that many number of beams will be created. Okay. So, that we have explained it in the last class. Now, it goes to the channel. So, now I am at the receiver side. So, this is the data model, whatever has been written in the above equation, that is the data model which will create exactly this particular beams. Okay. Okay. So, I will again come back to this Tx side for the exact some more optimization on the WRF part, because this WRF is a very critical component. That is the one which is a steering matrix now. Now, it is not a steering vector, rather I will say it a steering matrix. So, now what will happen to the Rx side? Now, before it goes to the Rx side, it has to go to the channel, right. So, now as you can notice, so I will create the data model for each and every beam, because if you notice that not every beam will finally it will not be received by all the users, right. Say for example, probably I may have one user here, somewhere here, and most likely this is the one which will be covering that. That is the one which will be covering finally, right. So, here when I say channel model for multiple beams, it is basically with respect to one particular users. Okay. So, I do not worry about what are the other users. So, it can be just say one of the ith users. So, okay. So, I just generalize it. So, it can be ith user. It can be just an ith user. Now, with respect to the ith user, how things vary? That means, when I say I am creating a transceiver model of my data at the receiver, it has to be with respect to one particular beam. Now, of course, other beams can create some interference, because they may have some sort of a side lobe. Side lobe can create, it depends on the distance. Obviously, if the distance is slightly larger, this side lobe may not create too much problems. But on an average, let us assume that it is one beam that is incident upon one particular user. So, now with respect to this user, I am modeling it. So, to me it is as if like nobody else is there, just one beam is created. So, what does it mean? It means that to me these things are just off, these are all off. Off in the sense, it is not off with respect to the ith user, with respect to the ith user they are off, obviously, because they do not reach. So, I do not care, I do not consider. So, how do you view it? How do you view this whole system? It is like one beam is coming and the data is just received by one of the user there. Okay. So, let us now proceed how we can model that. Okay. Now, I am at the receiver side. Okay. Now, suppose it was one beam. Obviously, I am getting one beam only. So, it is just like one beam coming and I have multiple antennas sitting there. Okay. And let us say I have NR number of beam forming antennas sitting there. Now, these NR antennas are also RX side beam forming. They need not be the signal of the combining part. So, they are basically meant for RX side beam forming. So, what is RX side beam forming? So, what is the purpose of beam forming? If you just look at beam forming is mainly it channelizes the power, right, to a certain direction. That is the beam. So, the purpose is that obviously it boosts up the SNR, it boosts up the received signal gain. See, that is the purpose. When I have multiple antenna at the receiver, can it also do the same thing? Yes, of course, provided it depends on how you take the signal and combine them. Suppose n number of antennas are coming there at the receiver and I just transmit from one antenna. So, let us say I take a simple case, I come back to this example. So, there are say I have multiple receive antenna NR and let us assume I am just having one antenna at the transmitter and it is isotropically radiating. Okay. And so, from a DSP point of view, I am just sending one data, right. So, what is my received data model? Everything from DSP, do not bring the RF and analog part there, everything you think from signal processing point of view. If I send XN through isotropic antenna and I am getting the signal received at multiple receive antenna. So, what is the data model? Data model is very straightforward, right. I mean, you may have noticed it. This is Y bar. Y bar is the received data vector at each and every antenna. So, I just stack it together. So, this would be H1, H2, these are my channels, whatever you think of, either it is a millimeter wave channel or it is a normal channel. I mean, there is no difference, just that how you approximate it, right. So, I am just generalizing it into XN plus I may receive a noise vector figure, right. So, now this is my data model, right. So, now ultimately I have multiple choices to decode the data, right. I can create some sort of an equalizer, okay. I can create an equalizer. I can create an equalizer to detect the XN. So, what is my final data model? Final data model will be Y bar is equal to some H bar X of n plus V bar. So, can I create an equalizer? Yes, there are multiple choices for equalizer like least square, like zero forcing, like MRC, MMSE, LMMSE, anything, whatever. So, I can find out some sort of an equalizer vector W. If I multiply this with Y, then I will get back my XN. So, that is the way to proceed. This is one way of doing. If you want to do an ML decoding, you can do an ML decoding. So, you have to in that case what you have to do if it is an ML decoding. So, why I am talking all this? Because this will be required at the millimeter wave also. How do you finally receive the signal, in what sense you receive it? So, if you do a ML decoding and the data is a Gaussian, so what is the data model? It will be Y bar minus H bar XN. So, you minimize this distance mod square, you minimize this distance, but it is a vector distance. So, it is a 2 norm of a vector, error vector, and over all possible value of your XN. So, if it is some sort of a constellation, you take which constellation it has been picked up and then you say, okay, this is what the value is. If it is ML, if it is not ML, if it is some other way of detecting like equalizer based detection, you can create an equalizer W. And how do you design the W? You can design W based on several criteria, design W based on One is MRC, maximal ratio combining, it can be LMMSE, and so on and so forth. Based on what cost function you want to optimize for, it can have it. Now, I would prefer any one of them. So, at the end of the day, what is this W? So, if it is say you do not want to do equalizer based, if you do not want to do an ML based decoding, sometimes it may be slightly tougher for a search point of view. If you want to do a simple linear equalizer based detection, what exactly you do? You do some sort of a MRC or some sort of an LMMS. So, what is this W? W is some sort of a vector whose length is equal to NR cross 1, because I have at the receiver, I also have NR number of data. Okay, here NR number of data. So, now why I am talking all this? Because the same thing I will just carry forward to my millimeter wave as well. So, now the point here is that I am at the receiver. So, when I am at the receiver, I have to do some sort of jugglery such that I can get back my data. That is my ultimate intention. So, in this particular example, whatever I have given you, it is kind of a isotropic antenna from the transmitter side. Now, if you bring in the beamed case, it will not be two different case. Okay. So, it is your choice. How do you design the W? So, you multiply the W and you get back your data from your XN. Now, this W, the choice of this W, either you can do it in digital domain, that is preferable, right, always, because if I receive a Y here, this is more of a digital data that I receive it. So, which means that from each and every antenna, I have to prepare a digital data, right. So, if the NR is say 100, what does it mean? What does it mean? So, what is the actual circuit that will be coming into picture? So, at each and every antenna, I have to put one LNA gain factor, then I have to I have to demodulate the signal, then I have to pass it through a bunch of LPF filters, the standard demodulation technique. Then it has to go through an ADC, this is your complex data, this probably I, this probably Q, you get 1 Y vectors fast data probably. Now, like that you may have a repetition of the same circuit for NR time. Same thing you repeat it and you get here Y NR. Now, this whole thing you call it Y vector. This is one part, because I am operating in a DSP domain, right. This precisely I was operating on, right. This is what my point was. Now, this is tougher. Now, this you have developed the equalizer based on some criteria and you get W as some complex number, and then you multiply this W with Y and you get back your Xn, fine. Or if you want to do ML, you can do all this, but at the end of the day, this is the circuit. So, which means that if NR is kind of say 100, you need that many number of RF chain and analog chain, right. You need that many number of LNA, which is an RF circuit, that many number of it is actually two times of your demodulator. So many complex analog and RF circuits are present if I want to do the W in the digital domain. So, now once I get this Y bar, I multiply this with a digital W star and I get back my Xn, that is fine. But the point here is this whole thing is happening in the digital domain, and precisely I do not want to do that in a millimeter wave context. Now, this is okay as long as you are in the normal domain. So, how do you design this W? There are many ways, as you can see. You can either say MRC, maximal ratio combining. You know what is MRC. If you do not know, I can just for your convenience, I can explain it what is MRC. This is basically simple, I mean it maximizes the SNR in a non-Bayesian framework, and and in fact it is nothing but the least square here. So, what is exactly an MRC? So, if you have a channel here seen at H1 versus if you have channel here H of NR, what you do, you multiply this data. I am assuming you digitize it and multiply it. So, you multiply this data with H1 star, multiplies this data with HNR star. Okay. Just multiply it. Then what happens? Then you just add them up. And what you get is a very nice form you get. So, basically here at this stage, whatever your data, that is your y bar, right, after your digitizations. Then what I do? I am multiplying with an equalizer. Now, I am saying that each and every equalizer is nothing but whatever channel you are seeing on that particular antenna, just conjugate it and multiply it. So, what happens? So, you have y bar, okay, and you multiply this y bar with conjugate of the channel. So, what happens? Let us see. So, this is your y bar. So, let us say and h bar, you conjugate it. That is what this particular. So, which means that here my w is nothing but your h, because I am conjugate and multiplying. So, w will be your h. Okay. So, what happens here? So, what will I get? So, what was your y bar? Y bar was h bar x n plus, that is a v h star, but that is okay. This is kind of a equivalent noise. So, this becomes x n. Now, this will be your total channels norm square, right. First, let us call it v 1 dash. Now, you divide this. Now, next you divide this whole thing by h mod square. What will you get? You get x n plus v 1 divided by normalized channel square. So, this statistics won't change much. So, now this will be something like you get R n is equal to x n plus something like that, or in a very simple sense, after all this MRC you get a data model which is equal to x n plus some normalized v 1, something like that. It is not even a vector, it will be some square. Now, this is the data model that comes into picture. Now, you can just do some sort of a simple search and find out what exactly the x n is. So, this is so this mechanism will boost your or maximize your SNR. Now, this is one type of equalizer. You can have some other equalizer. If you have say MMS equalizer, LMMS equalizer, now instead of H1 star something else will come into picture, but that is okay. That is not what I am trying to understand, make you understand here. What I am trying to understand here is that at the end of the day you have NR number of antennas, digitize them and you have to multiply them with an equalizer, equal number of equalizer. If there are NR antennas, because you get a y vector whose length is also NR, and you get to multiply it with a NR number of some complex coefficient. If you multiply it, you get some data and then you do a simple detection. So, you get back your x n. Now, the point here is that what all you are doing is in the digital domain, right, because you are multiplying with w, everything you are doing it in the digital domain. But if the NR is large, and that is typically the case when you have millimeter wave, how do you solve such problems? Because this will be tougher. You cannot just go by this mechanism. Okay. So, can I do some sort of a simpler mechanism by which I can in the RF domain, when I am actually in the millimeter wave, how exactly my RX side would be. So, if you look at the TX side, some part was done in the RF, some part was done in the digital side. Okay, and you know the obvious reason, because when I create a phase difference, want to create a phase difference, I have to get into the RF domain. That will be better. So it was a hybrid. So similar approach I also have to take it in the digital domain, in this RX part of the millimeter wave, because your number of antennas are huge. So you cannot afford to do everything in the digital domain, because your components, number of components, if you look at, if you just leave it like this, each and every antenna needs that many number of, you know, RF and analog chain, and it will be repeated n number of times, it will be repeated. So the cost of the, you know, the IC chip, the cost of the complete system will be very high, and also the power. Look at the power requirement, it's very high power requirement, right, because each and every point you have a demodulator, you have a low pass filter, you have an ADC. So on a die of you know, a system on a chip, putting so many ADC, putting so many LPF analog, and putting so many RF circuits are not advisable. You can't really do that so easily. So the better solution is that, can I move some of my equalizing concept into the RF domain? Okay. So that's the point that we are trying to make it when I am in the millimeter wave, because I am completely in the RX now. So the whatever mechanism I have explained here, can I see if some of them can be pushed back into the RF or not? Okay, and let us understand that. Now, let us understand from a single transmit antenna point of view, because that will be easier for explanation. So if you have, let me have one more antenna here. Okay. So I have n number of antennas, okay, and let us have the same thing. Let us have, it is a isotropic antenna. It really does not matter whether it is isotropic or a beamed antenna. Even if you have a beamed antenna, I do not mind it. Okay. So let us have one antenna which is a beamed antenna, and this whole beam is getting received by this particular antenna. These are the antenna. Now, I am not physically creating the things notion here, because in the RX side I have taken space, but in the TX side you can see the beams becomes wider. It is not the case, actually the beam can be even narrower also, because this distance is really small distance and this distance is really very large distance. Okay. So it is just for the understanding purpose. So it really does not matter whether it is a beamed antenna or it is kind of a isotropic antenna, because if it is a seesaw case, it is as if like one antenna sitting which is creating a beam, right. I think you have understood by this time. Okay. So physically there may be multiple antennas, but it is like one antenna sitting, equivalently one directed antenna sitting creating a beam. So I am talking of that kind of scenario. So even if there is a beam, I do not mind it. Okay. So the point here is that we are in the receiver side, and how exactly, how much or what we should do to avoid too many RF components, too many analog components, especially when my NR is very large. So whatever I have explained so far, you can do very well when you have a less number of receive antennas, say like a 4, 10 kind of things. Now you have when you have 100, you cannot have that. You have to minimize the number of components. So what is the best way to do that? Okay. So best way to do that is the following. So I take the approach of any equalizer. It does not really matter what equalizer you are finally taking up. Let us take, I am taking a MRC equalizer, or I can take even an LMMS equalizer. It really does not, again I am repeating, it really does not matter what equalizer you are taking. At the end of the day, there are n number of complex coefficient. So I do not want to bring these terms at all. I mean, you can find out lot of papers and lot of materials where people use these terms MRC or LMMC or anything like that. I do not want to prefer use this term, because to me it is nothing but some complex number. Okay. So at the end of the day, I have to multiply the data stream with a complex number. So let us generalize it. So let us say my complex number, as we have described it in the context of earlier case. So let us have this is the one which I get it, whatever technique you use, either you take an MRC. If it is MRC, what will be the W1? Nothing but the channel. If it is LMMSE, channel plus something, that is all. Okay. So, it is a complex number. So, if it is a complex number, what should I do? So, what I do here is that I just put, now I have to multiply it, right, because this is the one which I would like to have it. Now, here is the catch. If I multiply it, I mean you can say, okay, I am bringing up the RF signal, why don't you just multiply this RF signal with a multiplier called W1. So, that means what you are essentially saying that, so you have to multiply with W1 star, right, because it is a conjugate part. This is what I have to do finally. Okay. So, because that is the notion I am taking it, and to multiply the W1 star there. So, now the question is that can I put a multiplier directly there? Do I really need to put a multiplier there? Okay, because I want to avoid the digital part. Now, if you say, okay, do everything in the RF, then does it mean that I just put the multiplier in the RF domain? Now, my dear friends, it will be very difficult to put a multiplier in the RF domain, okay, because it is a complex number. Having a complex number multiplier in the RF is not an easy task to have it. So, what is the best way to do it? So, each and every W1 can I think of, it is a complex number, right. So, let us say the Lth one, Lth coefficient, can I have it like this? Something like that. What does it mean? It is a complex number, has a magnitude, has a phase, right. Obviously, any complex number has that. So, I split that. I said, okay, I have this which is a gain, can I call it a gain? This part I call it a phase. Now, mind it, that phase e to the power j whatever angle omega l I have written, that is in terms of the digital view. Again, your views is still digital, it is just the circuit point you are thinking. So, it is like a phase. So, I split that omega l or W L as gain and phase, right. Now, in the RF, moment I think this way, slight reprieve can happen here. I have a gain. How do you implement a gain in RF? It's kind of an amplifier, right? Any gain, how do you implement a gain in any circuit? It's an amplifier, right? It's an amplifier. So, that means, does it mean that I need a RF amplifier? Well, every antenna has an LNA, low noise amplifier. So, that is usually there anyway. So, I can take that same LNA, I can make use of the same LNA and push the gain there. So, which means that this multiplier, whatever I have drawn there, instead I just make a small change here. I make a small change. What is a small change? Each and every antenna is anyway fed through a LNA. Okay? Now, which means that every antenna anyway comes with a gain circuit, it is an amplifier. So, that is there anyway, because every antenna may have a different gain or may have a gain disturbance. To improve that gain, I have to have an LNA. So, that part I cannot avoid it. Okay. So, I have an LNA already sitting there. So, this LNA has a gain to improve the the sensitivity of my ADC level. So, I push this gain to the LNA itself. If this gain was already, if the LNA already having some gain, I push the another gain. So, which means that now this amplifier, whatever LNA is there, this gain will be pushed it here. So, if I take this is my Lth antenna, this Lth antenna, whichever the default gain the LNA was having, I put another gain there. So, it is easy to do that, because that gain is just a factor. Say it is say 1.2 or 0.3. So, I push that gain back to the LNA. So, it is easier to do. Okay. Second part was a phase. Okay. What should I do? I can just put a phase shifter here. That is all I will do. So, that means the gain part I push it to the LNA, and phase part I implement it as a phase shifter. Now, is the phase shifter an easier task to do in RF? Yes, because in the TX circuit also we have done a phase shifter, right, for steering. Here also I put the phase shifter there. Okay, I put the phase shifter there. So, I am multiplying definitely, I am multiplying with the W, but I am multiplying in a very intelligent way. The gain part I push it to the default LNA and only the phase I created as a phase shifter, that is all. That is the only job I will do. Next, what should I do? Now, you look at what my intention is. I want to omega now this y is kind of virtually like a RFY, right? That is what, because this W is now in the RF, but obviously I will view it from the digital domain. Now, this W star y, what does it mean? This is a vector multiplied by another vector in a inner product way. So, which means that this will be omega 1 star into y 1 plus omega 2 star y 2 plus omega n r star into y n r, right. These individual multiplications are done this way. What is left? I have to add them up, because that is what it is saying, right? It is addition. Everywhere there is an addition. So, all these components I have to now add up. This n r, I have to add up. So, what is the last stage? Last stage is that if I go up, these are my antennas, these are my antennas, this is my LN again. One second, let me change the direction of my antenna, because I am in a receiver data. So, this is my NR number of data. What I do? I already have an LNA. I am making use of the same LNA for my gain. So, this is my LNA part. Okay. Then I put a phase shifter. I just redraw the circuit. I do not want to delete the other content there. Then what I do? I just add them up, right, because this is what it is suggesting me. This is what it is suggesting me. After multiplication, I add them up. So, I put a adder. Now, what is this adder? Is it in RF domain or digital domain? It is in RF domain, right, because I have not put ADC. Now, I get only one data stream. Whatever I was writing, right, here, this Rn, instead of Rn, I think of its Rn's RF version. This is what is coming. So, this is the RF data. This is still in RF domain. Now, this I multiply with the I demodulate. This one I will just demodulate. LPF you put it, LPF you put it, low pass filter. Then we have an ADC, we have an ADC. Now, this one will give me Rn. What is the data model here? This Rn is still not Rn, because it is just multiplier, but that is okay. It probably H square. This one V1 bar or some V1. Let us not worry about what is the noise here. This is what is coming. Now, in the digital domain, you just divide it by H mod square and do the rest of the processing. But now you see, when I do this in the millimeter wave, I have to do it in the millimeter wave, because now you look how many RF components I am having. Just one phase shifter, sorry, not one, NR number of phase shifter, NR number of LNA, which are anyway there, but the demodulators, LPF, ADC, they are bulky circuit, I just have one. Provided my data stream is just one data stream, it is like a seesaw. So, it is as if like I have sent X1, it goes through all the transmitting channel blah blah blah, and then finally it comes here and my data model becomes just a single one. It is a seesaw case. That is the reason why I call it seesaw, because I sent one, and but when I receive it, through all the processing I get back only one data stream, and from there I will extract Xm, that is okay. So, now this concept is very helpful, because this is the one which will be also extended to the MIMO case. Okay? And you can see this particular proposal does not require so many ADC, just one set of ADC, of course couple of ADC, because you have an I and Q, one pair of RF circuits and one pair of LP circuit, RF demodulator and one pair of LPF, low pass filter. I don't need NR. So, no matter whether your NR is 100 or 1000, I still need just one set. So, this is what is convenient for millimeter wave. Okay. Now, I stop the class today here, and in the next class I extend the same concept for the MIMO case, whatever we have discussed in the transmitter side. Now, we have already started the receiver side. Now, this is for a single single XN case. Now, if I have multiple XN case, if I have X1, XN, multiple such XN, what will happen to that? That will be explaining in the next class. Okay. So, in conclusion, we have kind of completed the and the reference will be same as what we have. Thank you.